So this is chapter 18 and we have to work out the problems on electrostatic charges. And so we journey into the microscopic world where we talk about atoms, all of them being neutral, but having an equal amount of positive and negative charges. And the electron has the basic quantity of charge, which is 1.6 times 10 to the negative 19 coulombs. And all other charges are integral multiples of this electronic charge. Here we have problem number 1 coming up in chapter 18. So this problem talks about common static electricity involving charges that are really small, ranging from nanocoulombs to microcoulombs. Nano is 10 to the negative 9 and micro is 10 to the negative 6. And the question says, how many electrons are needed to form a charge of negative 2.00 nanocoulombs? And B, how many electrons must be removed from a neutral object to leave a net charge of 0.500 microcoulomb? So you're given the total charge, which is negative 2 nanocoulombs, and you know the charge of an electron. So what we got to do is just divide the total charge by the charge of the electron, as given by this formula. Q is equal to N Q sub E, where N is the number of electrons to be removed. Q sub E is the charge of an electron. So rearranging that, you get the number of electrons as the charge divided by the charge of an electron. Remember, negative 2 nano is 10 to the negative 9. And here is the charge of an electron. So when you divide it, you get 1.25 times 10 to the power 10 electrons. So such a large quantity of electrons is to be removed. It has a net charge, so it doesn't say if it's positive or negative. I just assumed it to be negative. So again, divided by the charge of the electron, and you get a large number of electrons have to be removed in order to charge it. So now in question 2, we have a 50-gram ball of copper having a net charge of 2.00 microcoulomb. What fraction of the copper's electron has been removed? So now, since the question says what fraction of the copper's electrons has been removed, first of all, we need to know the total number of electrons that exist in copper, and then we need to know how many electrons have been removed, and then take the ratio. So in order to find how many electrons exist in copper, we're given that each copper atom has 29 protons and that copper has an atomic mass of 63.5. So let's first find out how many electrons there are totally in a 50-gram ball of copper. Of course, it's going to be a big number. So when we try to do that, we know that the number of moles of copper is the total mass given by its atomic number. So that's how we find the number of moles, because the moles is the molecular weight expressed in grams. So the total mass given is 50 grams divided by the atomic mass of copper is 63.5 gram per mole, and when you do that, you get the number of moles of copper. But then if you multiply that with the number of protons in 1 mole, okay, multiply that number of moles with the number of protons in 1 mole, you will get the total number of protons. And for that, you got to go number of moles times the Avogadro number. What is Avogadro number? Avogadro number is the number of atoms in 1 mole. So N sub A is the Avogadro number. So that gives you the number of atoms in 1 mole, and then little n is the number of moles, and then you've got to multiply with 29 because each copper atom has 29 protons. And so finally you get the total number of protons as 50 by 63.5. Then that's the Avogadro number, 6.02 times 10 to the 23, and then 29 protons per atom. So that gives the number of protons as 1.375 times 10 to the 25. So that's the total number of protons, which should also be the total number of electrons, because the number of protons is equal to the number of electrons. All right. So that's equal to the number of electrons. Next, we need to find out how many electrons have been removed, for which we do it like we did the first problem, the total charge divided by the charge of an electron. So the total charge is 2 microcoulomb, so 2 times 10 to the negative 6, and divided by the charge of an electron, and you get 1.25 times 10 to the 13. And when we divide that number, you get the number of electrons removed divided by the total number of electrons. So we now get the fraction. And that happens to be 9.09 times 10 to the negative 13. This problem deals with Coulomb's law, where you have the formula for the force acting between 2 point charges kept at a certain distance. So in this question it says, how far apart must 2 point charges of 75.0 nanocoulomb be to have a force of 1 Newton between them? So the 2 charges are 75 nanocoulomb each, and the force between them has got to be 1 Newton. And what is the distance for creating that force is the question. So the formula from Coulomb's law is F is equal to K Q1 Q2 by R squared, where Q1 and Q2 are the charges, R is the distance between them, and K is a constant. Now rearranging, you get this for the equation. You make R squared the subject, which is K Q1 Q2 divided by F, and then which means R is going to be square root of the whole thing. Okay, so K is a constant in free space or air. It's 8.99 times 10 to the 9. And then each one of the charges is 75 nanocoulomb, which is 75 times 10 to the negative 9. So you got to square it because there is Q1 times Q2, and then divide it by the force, which is 1. And when you calculate that, you get the radius, or the distance in this case, to be 7.11 times 10 to the negative 3 meter. In this question, we have a test charge of plus 2 microcoulomb placed halfway between a charge of plus 6 microcoulomb and another of plus 4 microcoulomb separated by 10 centimeters. So you have plus 6 and plus 4, and then exactly midway between them you have the test charge of plus 2. What is the magnitude of the force on the test charge? And what is the direction of this force? Is it away from or is it towards the 6 microcoulomb? Now let's set up the diagram and see how it is. So here are the 2 charges, Q1 and Q2, 4 microcoulombs, 6 microcoulombs, and then you have the test charge of 2 microcoulombs exactly midway. The distance between them, between the charges, is 10 centimeters. So now when I write F 2, 4, that's the force on the test charge by the 4 microcoulombs. The 4 microcoulombs is positive, the test charge is also positive, which means there is going to be a repulsion. So the force on the test charge is going to be away because it's going to be repelled. And that's given by Coulomb's law as K Q1 Q2 by R squared. So 8.99 times 10 to the 9, which is the K. And then you have Q1 times Q2 divided by the distance squared. So why is it 0.05? Because this total distance is 10, but this is only 5 centimeters. And when you change centimeter into meter is 0.05. So when you do that calculation, you get 28.8 newtons. Next, we need to find the force by the 6 microcoulomb. Remember, the 6 is also positive and this test charge is positive. So once again, the 2 microcoulomb is going to be repelled. So the 4 microcoulomb is pushing it one side, the 6 microcoulomb is pushing it the other side. All right, and let's find that force. The force on 2 due to 6, once again by the same formula. That's K, then you have Q1, and then you have Q2. So it's 6 and 2 now. So, and then the distance is 0.05. You get that as 43.2 newtons. And what is the net force? The net force is going to be the difference between them because they are acting in opposite directions. So that's why you take the difference, you get 43.2 minus 28.8, which is 14.4 newtons. Now what is the direction of this force? You see that the bigger force was the 43.2 newtons. So that means this force is going to be away from the 6 microcoulomb, because the 6 microcoulomb was pushing it with a bigger force than the 4 microcoulomb. The next problem says at what distance is the electrostatic force between 2 protons equal to the weight of 1 proton? At what distance is the electrostatic force between 2 protons? Now, we can find that using Coulomb's law and set it equal to the weight of a proton. How do you find the weight of an object? It's mass multiplied by acceleration due to gravity. So, set the Coulomb force equal to the weight. F is K Q1 Q2 by R squared, which is equal to mg. And what is Q1 and Q2? Both are the charges of a proton. So we know the charge of a proton is the same as the charge of an electron. And we got to find the distance. So I'm making R squared, or rather R, the subject. And then you plug in the value of the constant. Q1 is the charge of a proton. Q2 is the same. So you can just square it. Divided by the mass of a proton will be given. It's 1.67 times 10 to the negative 27 kilogram times 9.8. You solve that and you get 0.119 meter. Now this problem is kind of similar to the previous one, but with a subtle difference. Here you have point charges of 5 microcoulomb and negative 3 microcoulomb, and they are placed 0.250 meter apart. So you have the 2 charges. One is positive, the other is negative, and you're given the distance between them. The question is, where can a third charge be placed so that the net force on it is 0? So you got to place the third charge somewhere so that the net force on it is 0. If the net force on it has got to be 0, then that means the forces due to 5 microcoulomb and negative 3 microcoulomb have to be equal. They have to be equal and opposite, so it cancels out. All right, so here we have the setup. That's a 5 microcoulomb. You have the negative 3 microcoulomb, and then we know that this third charge has got to be Q. It has got to be outside. It cannot be between them. Now, why can't it be between the two charges? Because if you put this Q between these two charges, the forces will not cancel out, because the 5 microcoulomb will repel it and the negative 3 microcoulomb will attract it. So you see the forces are both in the same direction and will not cancel. But if this charge is kept here and away, further away from the stronger charge, you know that this charge is going to be attracted by the 5. Repelled by the 5, attracted by the negative 3. Okay, again, this charge will be repelled by the 5 because both are positive, but it will be attracted by the 3 because it's negative. So there is a chance for those two forces to be equal and they are opposite. So we just need to set those two forces to be equal to each other, or set their sum to be equal to 0. So the total force, must be 0. So that's what I've done here. I've set the total force to be equal to 0. I've taken out the KQ, and here are the distances. If I take this distance as R1, and this distance as R2, and this distance as D, we know that D plus R2 is R1. D plus R2 is R1. It's given in the diagram. So I'll be able to substitute one for the other. So I've taken out KQ here. You have this, and then, like I said, R1 is R2 plus D. So, which means Q1 by R2 plus D whole squared should be, see, instead of R1, I'm substituting R2 plus D. And I'm setting that to be equal to each other. Okay? Why should they be equal to each other? Because we know K times Q cannot be 0. This has to add to be 0, which means that the magnitudes of these two must be equal. Okay, and then plug in what we know. We know the charge. We're trying to find R2. We know D is 0.25. Cancel out the negative 6's from both sides. Take the square root, because I'm trying to avoid the squares. So take the square root on both sides. So you got square root of 5, square root of 3, and then this whole square disappears. All right, even here the square disappears. So now cross multiply. All right, cross multiply, which is what I'm doing next. Yes, there are some math steps that you got to do. Collect the R2 terms on one side and then solve for R2. When you do that, and if you are careful, you're going to get 0.859 meter as the distance of that test charge from the negative 3 microcoulomb. Question is about electric field. So it says, what magnitude of point charge creates a 10,000 Newton per coulomb electric field at a distance of 0.250 meter? How large is the field at 10.0 meter? So what do you mean by electric field? Electric field is the force acting on a +1 coulomb kept at any point. Now that's very important. So whenever you're asked to calculate the electric field at any point, you have to imagine that there is a +1 coulomb kept at that point. So here we got to find what magnitude point charge creates that field. So the field is given, you got to find the value of the charge. And so we go straight to the formula. The electric field is given by KQ by R squared for a point charge. You're asked to find the charge, so make that the subject, and then the electric field is 10,000 Newton per coulomb. The distance is 0.250 meter, and K is the constant. So when you plug in all those numbers, you get 6.95 times 10 to the negative 8 coulombs. Next, you got to find how large the field is at 10 meters. So now you already got the charge, you got the value of the charge, You just got to find the magnitude of the field. Again, use the same formula. It's more direct now. E is k cubed by r squared. Put the value of k. The point charge we already calculated is 6.95 times 10 to the negative 8. And now the distance is 10 meters, so 10 squared. And you get 6.24 Newton per coulomb. Okay. So that's how we do this problem. This is a problem where you got to calculate the initial acceleration of a proton in a very large field. It's 5 times 10 to the 6 Newton per coulomb, 5 million Newton per coulomb electric field. And such fields can be created by the Van de Graaff generator. So we just need to find the acceleration of a proton. Now, one formula to find the acceleration is finding the force and dividing by the mass, because acceleration is force divided by mass. So first let's find the force. Force is given by Q times E, where Q is the charge and E is the electric field. So in this case it's a proton. We know it has a charge as 1.6 times 10 to the negative 19, same as the charge of an electron, and then multiplied by the electric field, you get the force acting on it. Once you get the force acting on it, use force equal to mass times acceleration and find the acceleration. It's force divided by mass. So there is the force divided by the mass of the proton, again, which will be given to you, and you get a tremendous acceleration. Now remember, this is where you see that even a field is able to give that huge acceleration to a proton. That's the idea that we use in a television picture tube, for example, to swing the electron beam back and forth, because we know that the electron or the proton is going to be very much affected by the field, which means it's going to have a big acceleration. We have a problem here where you have a 5-gram charged insulating ball right there hanging on a 30 centimeter long string, in a uniform horizontal electric field. So the electric field is horizontal and it has a value, and we got to find the strength of the field. The charge on the ball is given as 1 microcoulomb, and this problem comes with a diagram. If you look at that diagram, you can see that the forces acting on the ball, number one is the weight of the ball acting vertically down, the gravitational force, the weight. Next is the electric force because of the field acting on the particle. All right, so those are the two forces. And then the third one is the tension in the string. So you got to have a tension in the string, which is T here. And because the two forces, one is along the y-axis, the other is along the x-axis, but this tension is neither along the x or the y, we need to break it up into its components. So you get T sine theta and T cosine theta, and you get that from the triangle. When you set up the triangle, you're going to get the same angle here, theta, and this becomes the adjacent side, while this becomes the opposite side. The opposite side is sine theta, the adjacent side is cosine theta. You should know this from semester 1. So now you have T cosine theta, which should be equal to mg, and you have T sine theta, which should be equal to the field, the force due to the field. So now we have T sine theta should be equal to F sub E, which we know is given by Q times E, and T cosine theta is equal to mg. So if you divide this by the second one, we're going to get tan theta, because the t's will cancel out, and sine theta by cosine theta is tan theta. That's just an easier way of doing it. The other method is you can substitute, find the angles, and then put it into the second equation, but this is easier. So divide one equation by the other. The left hand side becomes tan theta. On the right side, you just divide QE by mg. Okay, and then we got to find E, so we make E the subject, and you get mg tan theta by Q. The mass is given in grams, so you got to change it into kilograms. That's 10 to the negative 3, because 1,000 grams is a kilogram. You have G and tan 18 divided by the charge. The charge is 1 microcoulomb. Oh, I think I made a calculation mistake, but I corrected it, and it is 1.5 times 10 to the 4 Newton per coulomb. So I hope you understood this chapter, and I hope you first watched the lecture, understood the concepts, and then you worked out the problems, and then you've understood how these problems are worked out, and you should be good to go to take a quiz or even to take an exam on this chapter. Thank you. Wish you the best.